Engineering Senior Design Team 19054 is proud to present our project Seraph.
When disaster strikes, the ability for first responders to act is often limited due to connectivity issues and the physical destruction of roads and other infrastructure needed for emergency vehicles and personnel to deliver critical support and supplies into and out of the affected area. The ability to survey the disaster-stricken area without putting any lives at risk while also being time efficient is critical. This is where the Seraph, swarm of electro-optical recording aircraft for photogrammetry, a semi-autonomous drone swarm system dedicated to surveying a disaster area using the drone's optical camera and 3D modeling, comes in. The word Seraph is defined by the Oxford Dictionary as an angelic being, which is what our system is designed to emulate. The most notable requirements that drove our design were that the model shall be compiled from images gathered by a swarm of 2 to 4 drones, the central control computer shall initiate the flight of the drones, the central control computer shall initiate the construction of the 3D model, the Seraph drone data shall be downloadable to the central control computer, and the Seraph drone image collection capacity shall be scalable to cover greater than 60 acres.
We researched a lot about the different commercial drones available, as well as the model building and flight control software. We aimed to understand the data links that would be required, cost versus performance trade-offs, usability, and camera performance. We performed trade studies on drones, software, and control schemes. Here's an example of one such trade study. Following these trade studies, we selected the unique Mantis G as our drone of choice, Ground Control to serve as our flight control and mission planning software, VirtualBox to serve as the swarming engine, and Drone Deploy to serve as the system model building and viewing interface. The final Seraph prototype consisted of 2 unique Mantis G drones, a laptop, 2 external USB wireless adapters, 2 micro SD cards, 2 spare batteries, the charger, USB-C to USB-A cable, a 4-port USB hub, and a backpack for transportation. With our first responders in mind, we wanted to make the system as compact and portable as possible. This being the case, for the final production version, a system operator could carry up to 4 drones, 8 spare batteries, and 4 wireless adapters, the 4-port USB hub, and extra cables, all in a single backpack. To operate Seraph, first turn on the laptop with the USB adapters plugged in. Start VirtualBox and run the desired number of Ubuntu virtual machines. Open Ground Control in each of the virtual machines and the native laptop. Deploy the drones by first removing the gimbal clamps and unfolding the wings. Place the drones on a level open surface free of overhead obstructions and power them on. Connect 1 drone per virtual machine via their dedicated Wi-Fi signal. The drones will then be auto-detected by Ground Control and connected. Go to the Planning tab in each instance of Ground Control and open the desired mission file. Upload the mission files to the drones, return to the Fly View tab, and one by one launch each drone by sliding the Start Mission bar. The drones will then complete their flights autonomously and land at the designated location. Retrieve the drones and connect them to the laptop using the USB cable and pull the imagery from the 100 media file. Once the photos have uploaded, Drone Deploy begins constructing the 3D model. You will receive an email when the model is complete and is ready for viewing or export. Once the model is complete, you can view the model in Drone Deploy, see additional map details, make measurements, or export the model.
Once the drone swarm was created, the next step was determining the operation conditions of the swarm and establishing the performance envelope, which was done using test data and models. The first thing characterized was the amount of onboard storage that would be necessary to survey 60 acres. To do this, we found the average storage required per photo to be 7.51 megabytes and then modeled the number of photos to cover the 60 acres as a function of altitude. The maximum area that could be surveyed as a function of altitude was modeled using Ground Control, and the manufacturer respects it on the battery life of the drone. Comparing these models, we decided that 50 meters in altitude would be the best compromise between storage requirements, model detail, and total area surveyable. The drone velocity was set between 5 and 7 meters per second to minimize the motion-induced blur and maximize area surveyable. We then conducted several test flights to characterize the drone's battery drain at the different test speeds and validate the total area surveyable model. From this data, we extrapolated the value shown below. As you can see, flying at 7 meters per second increases the total area that can be surveyed by one drone and decreases the total mission time when compared to flying at 5 meters per second. The trade-off is that there is 40% more blur when flying at 7 meters per second. This value is imperceptible to the human eye at 50 meters in altitude. Following the analysis, we were able to determine that at both speeds, a minimum of 2 drones would be required to cover 60 acres, while taking only nadir images, 3 drones to cover the area with nadir and oblique images, and 4 drones to cover the area with nadir and crossing oblique images. With the analysis complete, we flew missions to compare the difference in model quality when using nadir images only versus when including oblique images.
Here we have a model of the neighborhood, built from drone imagery taken by the team, again viewed using Autodesk Maya. In this model, oblique imagery was included alongside the nadir images during model building, captured from the desert side of the neighborhood to avoid flying over populated areas. From here, we can see the effects of including the oblique imagery, which increase the three-dimensionalities of features and improve the qualities of the houses modeled from this side. This can especially be seen by comparing the desert side of the modeled houses to the street side, showing the vast difference in quality between the two.
Here you can see a side-by-side comparison of when the model was compiled using only nadir images and when adding crossing oblique images. As you can see, both models have the general structure of the building, while the crossing oblique model appears to have much higher resolution and the houses are modeled more accurately.
Our system requirements were almost exclusively verified through tests. These tests ensured that each of our subsystems, that is, our drone, central control computer, or CCC for short, and 3D model generators and viewer all worked within our standards. We looked for Boolean attributes of the system behaviors to verify if it would pass or fail. These results were recorded in our test data sheets just like this one shown here. For example, we looked to see if the central control computer was capable of communicating with at least one drone followed by two or more drones. When at least one drone was able to connect to the CCC, we would mark it with a pass. When more than one drone wouldn't connect to the CCC, we would mark fail. Most of our testing was done in Oro Valley, specifically at Wilson K-8 and Ironwood Ridge High School, while model building tests were done on personal laptops of team members where internet connectivity was available. These locations were ideal for drone flight due to the clear weather, and the structures and terrain there helped in determining the accuracy of our 3D models. Throughout the course of testing, we were able to verify all requirements. We successfully controlled two drones in flight simultaneously while having the central control computer controlling every aspect of the drone's flight with the control scheme, designed to be expandable to an even greater number of drones given additional resources. During testing, we were able to receive images and video wirelessly and through an SD card. However, the wirelessly transmitted images were very compressed and unsuitable for model building. All imagery was automatically geotagged with longitude, latitude, and altitude, and was able to be compiled into a 3D model using Drone Deploy. The constructed 3D model from the gathered imagery had a resolution of 5.08 centimeters per pixel, 3 times that of our required value ground resolution. The model can be navigated by changing the eye point location, azimuth, elevation, and zoom, or by placing GPS markers in the model and clicking on the marker. Finally, we were able to prove that we could cover an area of 60 acres through a maximum range test, storage analysis, and a flight time versus battery drain analysis.
Before we conclude our presentation, we want to acknowledge those that made this project possible. We would like to thank Northrop Grumman for sponsoring our project. Specifically, thank you Paul Sudoff, Dana Cordova, Jessica Couch, Michael Keene, Ray Rowley, Jonathan Edmonds, and Eric Moret for your support throughout the year. Additionally, we would like to acknowledge the help of our mentor, Bob Messenger, as well as the staff and the faculty of the College of Engineering. Finally, we want to thank the first responders that Seraph was built for.